We shall. You want to share my screen now with all of you? No, I'm not actually. What am I doing? I'm going to share my camera with you. Yep. All right. Let's move this fellow here today. What do you say? No, let's move it right there. All right, so you guys can see me there, you can see me there, you can. Let's begin. So we were doing Equilibria last time, right? And I hope that made some sense to you. You know, it was a fun class. I thought it was fun. I really thought it was actually a lot of fun. Yeah. And I sound the same at 1x speed, 1.5x speed. Sometimes I talk really fast, 1.5x speed. That's probably why I talk really fast. Yes. I do. Okay. So, anyways, let's begin. Equilibria. So, multiple screens in front of you. Okay. And chat. Let me just open the chat, and then I'll minimize this screen. All right. Close this also. Close this also. All right. Okay. So where were we at last time? Yeah. Okay, so let's begin after the chitta chatter. Okay, and we were doing reversible reactions, right? Now today what we're doing is, so today we're going to look at all the factors that affect equilibrium. The factors that affect equilibrium. Okay, so you could say, let's say factors that affect equilibrium. Now what I mean by affecting equilibrium is, I mean they generally affect the yield. Okay, the yield percentage. It changes the yield percentage. Some factors can increase the yield, some factors can decrease the yield, that kind of stuff. All right. Now what are these factors are? These are all the same factors that affect rate also. So the three factors we're going to talk about are concentration, pressure, and temperature. These are three factors that also affected rate of reactions, you remember? And because they affected rate is why they will affect equilibrium. Because remember, the equilibrium was what? The equilibrium was the point, the position in a reversible reaction where the rate of the forward and the backward reaction is equal. So what if you change the rate of the reaction of one side? That will affect the position of the equilibrium. It's like if you remember the analogy of you walking up an escalator that is supposed to go down. Now, like I said, that's literally a perfect example in physics about what a dynamic equilibrium is. That there is some change happening, but let's do this. There is some change happening, but you don't see it. It's like the boy going up an escalator and the escalator coming down. And if the rate is the exact same, meaning that the boy is going 2 steps above per second. So let's say the rate of the boy is 2 steps per second, which is very fast, 2 steps per second. And the escalator is also moving down 2 steps per second. So the rate of one direction is 2 steps per second. The rate of the opposite direction is also 2 steps per second. And since the rate are equal and in opposite direction, the boy is stuck in that same space in the escalator. He doesn't seem to be moving. That's an equilibrium. But there is He is moving and the escalator is moving. That's what happens in reactions also. The reactions are moving forward and backward, but they seem to be still because the number of molecules don't change. Now in this particular case, if you suddenly were to move faster, if this boy for a second says, you know what, for the next second, I'm not going to do 2 steps per second, I'm going to do 3. Somehow he does 3. Well, the escalator is still moving down at 2 steps per second. What do you think will happen? The position of the position where the boy stands will change. He will now suddenly be 1 step above, because he's going up 3 steps, but the escalator is coming down 2 steps. So in the next second, when the boy said, let me go 3 steps, so he goes up 3 steps, it comes down 2 steps, there's a net change of 1 step. So the boy's position changed. But after that moment, the boy says, okay, I'm tired now, I'm going to go back to 2 steps a minute, 2 steps a second. So after that, a gain of 1 step, he goes back into equilibrium. And that's generally what happens most times when you change one of these factors. One of these factors, and sometimes both, can affect the rate of both the forward and the backward. Okay? Now that's the problem. If both get affected, let's say that when the boy decided to go up 3 steps per second and the escalator at the same moment decides to go down 3 steps per second, in that moment, the net change is still 0. So you want those factors that will affect one side and not the other, causing a net change. And that will change what we call the position of the equilibrium, or in this case, the position of the boy, or in chemistry, the yield. The yield is just telling us how much product do we form. All right. And we had done the idea of products earlier. We had done in the last lesson that if you have a lot of product formed, your yield will be close to 100. If you have very little product formed, the yield will be close to 20-30%. So the position of the equilibrium can be given by the yield. All right. Okay. Anyways, so any questions so far? No, they will be, if the moment the rates become equal, they are back to equilibrium. Okay, the moment the rate becomes equal, they are back to equilibrium. All right. Oh, well, so when we change one side of the equilibrium, it's no longer in equilibrium, but eventually it goes back to a new equilibrium position. Because when we change something, the reaction tries to do the opposite of that. That's what I'm going to explain right now. Okay. Okay, 1 second. So yeah, 1 second. Let me just show you an example now. Yeah, I will. I am doing that right now. I thought, are there any questions so far? So let's take a look at the first effect. Let's take a look at the first factor. And what I'm saying is, I'm going to show you how changing amount or concentration. So how changing concentration affects rate. Okay? Affects rate and equilibrium. Now you've done obviously that if you increase concentration of something, the rate will increase, right? So let's take our fake molecules for a second. So remember we were using A and B last time to make AB, right? So let's call the forward reaction reaction 1 and the backward reaction 2. Can we do that? It's an equilibrium, so the reaction is going forward and is going backward. But let's say the forward reaction, to label it for me to speak to you easily and more frequently, I'll call it R1, and the backward reaction I'll call R2. Now the forward reaction R1 depends on the concentration of what? So basically the rate of R1, it's not even R1, the rate of R1 depends on the concentration of A and B. Because if you remember, rate of any reaction depends on the concentration. So if you have high concentration, the rate will be high, you know? Which is why, by the way, if you were to start this reaction, if you remember my example from last class yesterday, that if you had taken only A and B initially the rate of A and B becoming AB was pretty high. That means the rate of R1 was pretty high. But over time, as you develop AB, then its amount increases. Because its amount increases, the rate of the backward reaction, which is rate of R2, depends on the concentration of AB. Because what is R2? R2 is simply AB becoming A and B. And what is R1? R1 is A and B becoming AB. R1 is the forward direction and R2 is the backward. They're independent reactions. They just happen to be in equilibrium, but they're independent reactions. So R1 depends on the concentration of A and B. R2, the backward reaction, depends on how much of AB you have. So if you think about it, initially when you start off a reaction, you take A and B. You don't have AB. You don't have the product AB. You have the reactants A and B. So you start the reaction, they are in very large amounts. They are in the highest amount they can be, remember? Because they're starting off the reaction. So they're in the largest amount. You know, if you remember, we had 10 of each. And they would react very fast. So, you know, if you had take the example earlier, I had 10 of each. That's the highest amount. And in the first second, we said 3 of them react. And then suddenly, in the second, now you have only 7 and 7 left. But now you have 3 of AB. Now, what starts happening is, in the first second, these guys were 10 and 10. The rate was very high. In the second, now they become 7 and 7. So, if I ask you, what happens to the concentration of A and B after the first second? What would you say? Yeah, I'm asking you guys on those on chat. Okay. If I concentration decreases. Absolutely. You are right. I have this guy on YouTube telling me that I'm really weird. Why are you really weird? So appreciate the fact that you're sick and teaching chemistry. I don't know if he's being, polite or he was making fun of me. I don't know. So all of you are right. The concentration of A and B will decrease after the first second. So what happens to the rate of R1 after 1 second? So rate in second number 2. Rate in time of second. The second. Will the rate be the same as the first second or slower? I'm actually pausing to ask you. Slower. Good. So rate will be slower because the concentration decreases. And maybe so that decreases. Now let's talk about the backward reaction. In In the first second, there was no AB. So the backward reaction was nothing. There was zero. So literally in the first moment, the rate of the backward reaction was zero. Nothing. Nada. Right? Then now you have 3 of AB. So rate of R2 in the second compared to the first second of R2. What would happen to that rate? It will increase. It will increase. Absolutely. So R1's rate decreases, R2 rates increases. And then we had mentioned that there will be a time where both the rates are exactly equal. And when that happens, you have formed an equilibrium, right? That's what we have discussed. Agreed? So far, you all get that? You all get that? Yeah? Let's say that moment of equilibrium was 6, 6 and 4. So somehow the rate with 6 and 6 of A and B was of R1 at that moment is equal to the rate R2 when AB was 4. We did that yesterday. You guys said that you understood that part, right? I'm using actual numbers, fake numbers, but actual numbers, right? So at this moment, basically, if you have a box, and I'd like to make a container because we are talking about a closed container. So what we have in this closed container is we've got 6 of A's, 1, 2, 3, 4, 5, 6. 6 of B's, 1, 2, 3, 4, 5, 6. In fact, okay, no, I don't do that. And then let me say I'm using these circles to represent AB. Now, this is now an equilibrium. This is an equilibrium between A and B becoming AB. And in A levels, when you go there, you will actually calculate the mathematical position of this equilibrium. But in O levels, we don't do that. We're there right now. Okay. So now what that means is, unless I do something to this equilibrium, it will never change. It'll stay as is. Yes, some A and B will become AB, and at the same time some AB will become A, but the rate at which A and B become AB and the rate at which AB become A going to become equal, which means the rate of R1 is equal to the rate of R2. Remember, R1 is forward, and in my case, in R2 was reaction backward. So at this moment, these are equal, and what we have is a dynamic equilibrium. This is what we all did yesterday. Yeah? Do you understand this much? Sorted? यहाँ तक सही है? Because it keeps on happening. It's called dynamic. It's called dynamic because the reaction doesn't stop. A and B keeps on reacting to form AB, and AB keeps on reacting to form A and B. They don't stop. It just appears to have stopped. But in reality, the reaction hasn't stopped. It's just mathematically the numbers stay constant, so we call it an equilibrium, but the reaction continues. And it continues and it continues. At the molecular level, A and B are bombarding to have a successful collision to form AB, and AB is bombarding to have a successful collision to become A and B. If you remember the collision theory of rates of reactions. Yeah? Understood so far? Okay. Now, okay, one second. Okay. Now, what if I do something here? What if I suddenly say, you know what? Because remember, what does R1 depend on? R1 depended on the concentration of A and the concentration of B. Remember? The rate of R1. And the rate of R2 dependent on the amount of AB. Do you agree? For somebody asking कि A level organic पढ़ा दें या मेरे चैनल पे कोई 200 वीडियोस ए लेवल ऑर्गेनिक की पड़ी हैं यार, आप वो देख लें, वो भी बासी नहीं हुई हैं, वो फ्रेश हैं, वही सिलेबस अभी तक चल रहा है, वहाँ से पढ़ लेना. Yes, we'll do them. Yeah, I know, Saad. I have to stop figuring out how to disable this chat. You know, I really know. Okay, how do you disable this chat? Yeah. Anyways, moving on. Where was I? Now, what if I tell you that I suddenly say, you know what, Bilal, you have this equilibrium going on for days. Nothing is changing. Okay? So, what if we say that let's add some more A's around here. Look at my green. I'm throwing in suddenly a lot of A's. Do you see that? I've thrown these greens. So suddenly what I said is, you know what? Screw your equilibrium. No, it's there, but I suddenly add some A. Now when if I suddenly add some A, what happens to the concentration of A? I am increasing it. Now if the concentration of A increases, suddenly what will happen to the rate of R1? The rate of R1 will increase. Why? Because suddenly, even though I kept B constant, I suddenly increased A. And if you remember, if you increase the concentration of something, the rate will increase. So if I increased one of the reactants, the rate will increase. At this moment, now suddenly R1 is no longer equal to R2. R1 is now more than R2. And remember, when can the equilibrium establish? Because suddenly at this moment, R1 is greater than R2. So suddenly you want to be able to now say, okay, no. Now at this moment, there is no longer an equilibrium. So now, wait, I'm getting there, Saad. So at the moment I added A, in that millisecond moment, before it reacts to make AB, what happens is in that millisecond, in that moment in time, the rate of R1 is suddenly greater than R2. But then, as suddenly you make A more, you increase the rate of R1 reaction, which means you make more of AB. So over time, this starts to decrease and AB starts to increase, because now you're making more of AB. Because more of the forward is happening and less of the backward is happening. So what starts to happen is you start to make more of AB and you start to use up some of A and B. So with time, even though R1 was more than R2, R1 starts to decrease while R2 starts to increase. And eventually, there will be a time when eventually R1 will become equal to R2 sometime later. And again, a new equilibrium would have formed. Do you follow that? Okay. Great. So if you're following that, that's awesome, because I will talk about the equilibrium position in a second. Right now, I'm just talking about how that there was a certain rate, and the rate could have been 3 molecules per second each way. Suddenly you increase the rate for one, it goes to maybe 5, 6. But then it starts to decrease because now it starts to get used up. And suddenly over time, some of these, let's say 1A and one B and one more B decrease, and now suddenly you have, now there were 4 ABs, now at equilibrium now you have 6 ABs. You might even have say no, maybe one more A and one more B becomes AB. So now what I'm drawing is in new equilibrium position. This is a new equilibrium position. In this new equilibrium position, if you remember earlier, there were 6 B's. Now there are only 3 B's. There were only 4 orange dots. Now there are 6 orange dots. But there's a lot of A because you added A, you see. But now what happens to the yield? Because the yield is AB. So in this new equilibrium, the concentration of AB is more than before. Do you see that? Yes, Saad, you could say that. But I didn't mention the shift. The shift is not a word I have used yet. All right? Menahil, on YouTube, you would actually enjoy this class also, because this is also something that A-level kids don't understand about rates of reaction. So, you know. Yeah, so no, don't be sorry. I'm just highlighting the fact that I have not used the word shift purposely. Okay. All I've said is that there was a certain rate that they existed and equilibrium. Suddenly you added more A and the rate of the forward increased, but the backward stayed the same. But as you make more of AB, the rate of the backward starts to increase, and the backward starts to increase and the forward starts to decrease till they become newly equal again. And they become equal again because over time the A will decrease and the AB, which is the orange dots, will increase. And now it becomes equal again. But now you have more product than before. And because in the new equilibrium there is more AB, or more of the right hand side, or more of the product, we scientists or chemists say that the equilibrium is established again, but it has shifted to the right. Because now at my new equilibrium I have more of what is on my right. Yes, it has more of A also, but that A came from because I added it. Once I added it, the system tried to make more of AB. And short layers verbalize this as a principle, that if you add something, once an equilibrium is achieved, the equilibrium will shift to reduce that. So the moment we added A, the equilibrium shifted right to make more of AB and less of A. So there was more A here that I removed, by the way. There was 3 or 4 more A's that I removed. Why? So that it becomes AB. So I'll explicitly mention what the principle is, but I was showing you Abhi that if you increase one side, a new rate it happens, a new equilibrium position happens, and that new equilibrium position will have more of the other side. Now, for the exam, you don't have to say any of this. I'll tell you what you have to write for the exam. It's a very simple, straightforward thing that you can learn. But this was me trying to explain why it happened. And if you didn't understand this, then either you can watch this recording again or just focus on what I want to teach you next. Any questions so far? I hope. Yes, Hafsa, every single lecture is on YouTube, boss. If it's live streamed on YouTube, it is. In fact, what I do is I just upload the more concise version of the lecture once I have time, basically. Okay, just seeing who's also here. ठीक है. Okay. Now, the next thing. Sorry about that. So now let me summarize the principle very easily. Is that if a system is in equilibrium and an external change is applied, so any external change applied to an equilibrium is opposed by the equilibrium, That's the rule. It's very simple. Now you might say, what do I mean by this? Well, let's look at what I just did in the light of this explanation. I had A and B becoming AB, right? I had A and B becoming AB. They had already been at equilibrium at some point. Equilibrium was there, they were having fun, it's all there, yeah. So at some point in this equilibrium, we said from outside, hey, I like to have some fun. I increase A. So externally, I increased A by increasing its concentration. Square brackets mean concentration. So the concentration of A I increased by adding more A myself, by literally adding more molecules of A. So this principle helps you remember what's going to happen to the equilibrium. Now you got to take this principle for truth now. I've explained some of it. I don't intend to explain more and more because then you are going to A-level category. And I don't want to spend too much time on this. I want to end this today. So the idea is that if you increase one variable, the equilibrium will shift. Shift meaning it will either make more of one side or the other side. And so in my terminology, let's call the reactants the left hand side, LHS, and the products RHS. I find that it reduces bias in LHS and RHS. Left hand side and right hand side. All right? Okay. Hafsar, I don't know right now. All right? Message me on the Mighty Network platform. In the middle of me explaining something, you're asking me when can I? No. Yeah. Okay. So basically what I said was, if I increase the left hand side, the equilibrium will oppose that. So that means if I increases concentration of A, what I'm doing is I am increasing left hand side. So now what will the equilibrium do? So what will the equilibrium do? So this was external. By increasing A, I am increasing the left hand side. The equilibrium will want to do is the opposite, right? So what is the opposite? The opposite of increasing left hand side is decreasing left hand side. Wouldn't you agree? That's the exact opposite of increasing left hand side. But an equilibrium is not a human being. It can't throw out A. So the only thing it can do is it can either shift left or right. So what it says is, I made A, I don't want A anymore. So I'll take this A and I want to reduce it. So the only way to reduce left hand side is to go right hand side, is to increase right hand side. So it wants to reduce left hand side, but it can't. So it has to, the only way it can reduce left hand side is by increasing right hand side. That is by shifting right. And by shifting right, it has made more of AB, which means also the yield will increase. Do you follow this? Delaware, you are right, Delaware. Anybody alive on the Zoom chat? Yeah? All right? Yeah? Do you get it? Do you get it? Okay? Yeah, maybe? All right? No? Okay. Anybody? Okay, yeah, got it. So I don't know, I was asking. Any questions? No questions. Alrighty then. We continue. We continue with this. Now, what if I change the scenario? I said, you know what? Let's take the same thing. Now, I change my scenario. I delete all of this crap. And I delete all of this. So I've got the external, which I should move a little on top. Yeah. And I've got what would equilibrium do? So I've got two regions. Okay. So now let's do something else. Let's do something else. What, Saad? So in the opposite, when they move to the left, yield decreases. Yes, obviously, Saad. Yes. So let's show you example of that. So now let's say I say, you know what? I'm going to go to this equilibrium and I'm going to somehow decrease B. So when I decrease B, what am I doing? I am decreasing my left hand side. Now what will the equilibrium want to do? It'll want to do the exact opposite. It'll want to increase left hand side. Now the only way to increase left hand side is by shifting left. Now if it shifts left, meaning if it shifts left, then the right hand side will decrease, which means the yield will decrease. Do you follow? Saad, does that answer your question? Farwa, I'll send you notes separately. I don't have the notes, I'll send them to you. Yes. Is everybody else following? Haya, Farwa, Arisha, Ramesh, Rida, Saad. I said instead of increasing A, we decrease B. V meaning externally, after equilibrium, we have decreased B. Okay. What I did here was that I said, let's go back to the original equilibrium. But now instead of increasing A, let's decrease B. Now if I'm decreasing B externally, what it really is doing is I am decreasing the left hand side. And if I'm decreasing the left hand side, then the equilibrium will want to oppose that, do the opposite. So if I, as the external party, is decreasing B or the left hand side, the equilibrium does the opposite by increasing it. Now how can it increase one side? It can only increase one side by moving to it. It can decrease one side by taking it and making it something else. But if it wants to increase the left hand side, it has to then take the AB and make it A and B, meaning go left. And if it goes left, then what you're doing is you're decreasing the right hand side or decreasing yield. Do you follow now, Arisha? Yes, okay. Now let's change some more. Let's look at a new variation. I'm going to delete that. I'm going to delete that. I'm saying, okay, so now let's see if you guys can predict it. What if externally I say, you know what? Let's take out AB from the system. Let's take it out. At equilibrium, the equilibrium is already established. And let's take it out. All right? Let's remove it. Or let's take out a lot of it. What that means, technically speaking, is I am decreasing AB. So if I'm decreasing AB, what will the equilibrium do in the steps that I've taught you? So if I decrease AB, what will the equilibrium do? Awesome, awesome. I like the emojis. The emojis are nice, yeah? The emojis are nice, yeah? One says shift to left hand side, one says increase. Everybody has got different answer. See it again. See it again, guys. You're not seeing it. Remember, I'm saying that the externally it is decreasing AB. So word for word, just by decreasing the right hand side, because that's what I'm doing, I am decreasing the right hand side. What will the equilibrium want to do? It will want to do the opposite. What is the opposite of decreasing the right hand side? The opposite of decreasing the right hand side is increasing the right hand side. That's what you guys remember. Either you change this to the opposite side to make it opposite, or you change this to the opposite symbol. You can't do both opposites and call this the opposite. Either you can say the right hand side decrease. If the right hand side is decreasing, the opposite is the right hand side increasing, or the left hand side decreasing. You can't say the left hand side increasing, because that is two opposites, and that's called double negatives. That will cancel out. Okay, so that's why I said look at the steps I take. I literally take the same side and do the opposite with that side. If the external factor is decreasing the right hand side, I will say let's increase the right hand side. How can I increase the right hand side now? How can I increase the right hand side? I want to increase this side. I want to go right. So I shift right. If I shift right, what happens to the yield? Even though I have removed AB, the total yield percentage will increase. So AB will increase. Yes. Even though I've removed it, it'll make more AB. And that's what the real world does. Even if you have an equilibrium, we go ahead and remove some AB. And the equilibrium says, oh, you removed it? I'll make more of it. You keep removing it, I'll keep making more. You keep removing it, I'll keep making more. That's the natural way, or the more efficient way of getting a better yield from a reaction that is equilibrium. All right? You are very welcome, Yash. You are very, very welcome. Okay. Do you ask all the rest of you get it? Are you getting it? Absolutely. It's a defense mechanism. It says you do this, screw you, I do the opposite. You do this, whatever you do, screw you, I do the opposite. Absolutely. Saad, absolutely. That's it. It's like the equilibriums screw you. No. You already remember, Mason, we already have A and B. You see, it was an equilibrium. One way to make AB is to have more A and B. The other way is to take AB out. Now, who is so stubborn? One way to increase AB, we had seen that, to just increase this side and that will go right. Or the other way is decrease this side, it will still go right, because it's not like you had finished A and B. They had some amount of AB left at equilibrium. That's what equilibrium is. It's an equilibrium. There's still reactant left. And when you remove this, the remainder will say, oh, let's react. We need to make more AB. He took our AB. We need more AB. Let's go get some more, make some more. That's literally what happens. Okay? All right? So, in a very, very, very simple process, you have a left-hand side in an equilibrium and you have a right-hand side in equilibrium. And you really can only do 4 scenarios. You know, you can literally do only 4 things. You can either increase the left-hand side or decrease the left-hand side. If you increase the left-hand side, the equilibrium shifts right, yield increases. Then if you decrease the left hand side, the equilibrium shifts left and the yield decreases. Now, let's go to the right hand side. So the same thing, you can do the right hand side. You can increase the right hand side. If you increase the right hand side, the equilibrium will do the opposite, which is decrease it. It can only decrease the right hand side by going backwards. And it goes backwards. Remember, anything that goes backwards, yield will decrease, because yield is a measure of the forward reaction. So if it goes left, yield decreases. If it goes right, yield increases. And then what we do is we try to figure out which factors will make it go right and which will make it go left. The fourth was right hand side decreasing. So if I decrease my right hand side externally, remember these are all external, the equilibrium will then want to make more of my right hand side, which means the yield will increase. Yeah. I will do questions in the next class. Arisha, yes, on Thursday I'll do questions for this. All right. Do you follow this so far? Yes, so far so good. Okay, then we have another factor that I should explain. All right, now just give me 1 second. All right, now the next thing will take some time. Okay, so yeah. Wait, how will we differentiate? No, you will be given what left hand side. Let's take an actual molecule. So let's take an actual reaction. Let's simply take an actual reaction. And let's say that I have a reaction where I tell you that nitrogen reacts with 3 hydrogens to make 2 moles of ammonia. And there's an equilibrium already established. Now, if, let's say, additional hydrogen gas is added to the equilibrium. Now, there's already an equilibrium established. You are going to be asked what will happen after the equilibrium is established. So I'm saying after the equilibrium is established, if additional hydrogen gas is added to the equilibrium, you can explain what will happen. Will happen. Now, all you got to do is find the side hydrogen gas is on, and then are you increasing hydrogen gas or are you decreasing hydrogen gas? And that's the generic method basically. So where is the hydrogen gas? Go look for it in the equilibrium. Can you find it in the equilibrium? Wait, let's go into a treasure hunt. Where we found it. It is right here. It happens to be on the left hand side. So now what am I doing to it? Am I increasing it or decreasing my left hand side? The word is additional. What does the word additional mean? Increase or decrease? So I am increasing my left hand side. So if I, as an external factor, increase my left hand side, remember the equilibrium is fighting it. It does the opposite. So the equilibrium, so basically if left hand side is increased externally, the equilibrium will shift where? Shift to decrease it. How can it decrease it? So you have increased it. How will the equilibrium shift? The equilibrium will have to decrease left hand side. How does it decrease left hand side? By shifting right. That's the one way to decrease left hand side. If it shifts right, it means it makes more ammonia. Therefore, yield, which is about the right hand side, increases. All right? Do you get that, Saad? Saad Salman? It's Mr. Saad Salman. Saad Salman. All right, Saad Salman. All right, Saad Salman. Abdul Hanan. Hanan. Arisha Dilawar. Farwa Haya Maisam Rida. I am going to go now. I'm going to end this right now. This chapter takes a little longer than it should because it's a very complicated area. I am glad. I am glad. I am glad. Who the man? Me the man. That is it. Yes, it is true. They say there have been many questions asked about this. Who the man? And it has been discovered that I am the man. The man. Eh? Anyways, I'll see you guys next class. Mañana. I'll see you guys Thursday. Thursday we'll finish the other two factors and I'll do 2 past paper questions. All right? Yeah. I'm enjoying teaching O-levels after decades. Like the last time I taught O-levels was 10, 12 years ago. So yes, it's been fun. I think it was 2010 is when I taught O-levels last. So Mason, it's absolutely fun. Dilaver, absolutely fun. I was just teaching A-levels for the last 10 years, at least only. Now I got back to teaching O-levels also. So it's been fun. Thank you so much, guys. Thank you, thank you, thank you. Thank you for the time. Thank you for the audience. And what do we say? We say sayonara. Peace out, boys.